slides because it doesn't work. Only pointer works. Okay, right, now it works. My name is Stepan Poluyanov. I'm from the University of Oulu, and I'm going to talk about the atmospheric cutoff, and particularly for its altitude profile. So, studying cosmic rays, especially with the neutron monitors, we use the property of locations called the geomagnetic cutoff, and this is the major property of locations. So the Earth magnetic field defines the cutoff values defined by the magnetic field. So as high as 17 gigavolts at the equator region, and the geomagnetic cutoff is almost negligible in the polar regions. And here, at high altitudes, both at the north and the south, the intensity of the cascade of cosmic rays near the ground is defined mainly by the ability to register particles via the cascade is defined mainly by the atmospheric cutoff value, because in the polar region the geomagnetic cutoff is about 0. Okay, and then, so I guess you are all familiar with the development of the cosmic ray cascade in the atmosphere, where the primary incident particle collides with the ambient atoms of air, and many sorts of particles are produced. But since I'm talking mainly about the application to the neutron monitors, I'm mainly interested in this hadronic branch. So, and since the neutron monitors are instruments located at the ground, the range of altitudes available for us is something between the sea level to the altitude of about 5 kilometers. And here you see that the cascade gets stronger with the growing altitude, and it means that the atmospheric cutoff gets lower because we have a higher probability for particle to hit the instrument. So in this work published last year, me and Alexander Misha, we calculated the atmospheric profile, how the atmospheric cutoff changes with the altitude. And we applied two different approaches. We call it like one physical and another one instrumental, let's say. The first one is we use the giant 4-based planetocosmics code to simulate the development of the cosmic ray cascade in the atmosphere, and we hit the atmosphere with the monoenergetic beams of particles with the vertical and isotropic angular distributions in this range. This range was chosen because we know that one point. The atmospheric cutoff for protons at the sea level is about 1 gigavolt in rigidity, or about 430 mega electron volts in the energy. So we played around this energy range, and we checked the intensity of neutrons at the depth from 600 to 1000 grams per square centimeter, which corresponds to the altitudes from 0 to almost 4 kilometers. And the criterion for registration was we need to have at least one secondary neutron at this depth to get the cascade registered. And the second approach is so-called the instrumental, where we use the recently published neutron monitor response yield functions for different altitudes. And we define it, we use the realistic spectrum of for galactic cosmic rays, and we set the detection threshold. We derived it from the one reference point, as I told you, that we know the atmospheric cutoff at the sea level. So, about this physical approach, you see that this is the number of incident secondary protons from one cascade induced by energetic primary proton as a function of the energy of this primary proton. So we set this detection threshold, and this is how we estimated the cutoff. This blue line corresponds to the sea level, and the red one corresponds to the about 3 kilometers of elevation. And we also played with the angular distribution. We took the isotropic and vertical one, but this is more realistic for our case. And the second instrumental approach is a bit more tricky. We can theoretically calculate the neutron monitor count rate with this integral, where this is the yield function and this is the intensity of cosmic rays. This is just basically the differential spectrum. And we can split this integral with the integration limit, EC, the parameter, which just splits the integral to the main part where most of the counts of the neutron monitor are, and also the low energy reminder. And we also can normalize this, the reminder part, the low energy part, to the standard deviation, to the sigma, which can be also found from the total count rate of the neutron monitor, since the counts basically follow the Poisson distribution. And so here, this lower line is the this reminder integral as a function of this energy integration limit for the sea level. And we know that the atmospheric cutoff is about like this for this altitude. And we set this as the detection threshold for the neutron monitor. And so using the same threshold, we could find how the cutoff behaves with the different altitudes. These are different curves correspond to different altitudes. And this is the altitude profile for this for our calculations. So the blue curve is the atmospheric cutoff profile calculated with this physical, with the planetary cosmics. And here, the red curve is this instrumental way to calculate it. The main difference between these two curves is that the blue one assumes that we register every single neutron that arrive. And the red one, the yield function based one, it takes the imperfection of the neutron monitor as a detector into account. That's why it is more conservative. And it provides the higher values of the atmospheric cutoff. Yes, important thing is that nowadays we have only two instruments which have exceptionally high sensitivity to cosmic rays, because they are polarly located in the polar region, have practically zero geomagnetic cutoff, and they are also located at high altitudes. These instruments are the Dome C, Dome B at the Concordia station, and the South Pole neutron monitor at the station Amundsen-Scott, basically at the South Pole. And these are the values. As I told you, the atmospheric cutoff at the sea level is about 430 megaelectron volts. And you see that these neutron monitors have the atmospheric cutoff values reduced to 300 MeV. And in the second work published, not yet published, but it's just waiting to be released, the preprint is available, we took all existed and some proposed polar neutron monitor stations with the geomagnetic cutoff below 1 gigavolt. So we assume that the count rates of these instruments are mainly defined by the atmospheric cutoff. And we calculated this curve, the altitude profile, with the instrumental approach, and also calculated these particular values for the stations. So you see that most of the polar stations are located here because they are located near the sea level. Here we have this exceptionally sensitive Dome C, Dome B, a South Pole, and also old neutron monitor Vostok, which is not in operation anymore, and the proposed station Summit at the top of the glacier of Greenland. These instruments are exceptionally sensitive comparing to the main family of the points here. and they can cause the event. They are able to register so-called sub-GLE events, which are solar energetic particle events with particles with about 300 MeV. And there is also the station Sanaya, which is somewhere between. It's also quite highly elevated, and they also have sensitivity higher than the rest of the polar stations. And now another thing that we tried, these all calculations were done for the conditions when we do not have the solar energetic particle events. It is the condition so-called this GLE, GCR only scenario, when we have only galactic cosmic rays. But what happens if we assume that, take into account, if we consider, for example, the extreme case, if the GLE number 5 happens. So we did this calculation, the GLE number 5 from 1956 probably, yes. It was exceptionally strong solar energetic particle event, and it had two distinguished phases, the prompt, so-called the prompt component and the delayed component. So you see, we took some hypothetical neutron monitor at 700 grams per square centimeter. This is about 2.5 kilometers of elevation. And and you see how this remainder integral grows up, and this also reduces the atmospheric cutoff significantly to the lower, in the lower direction. So this is a list of the studied neutron monitors, and you see that almost all of them are at the sea level, and their atmospheric cutoff is around 400. But during the GLE scenario, extreme, this value can drop as low as to lower than 300 MeV during the hard prompt component, and even lower to 130 MeV during the delayed phase of the GLE. So I want to say that the GLE number 5 is quite an extreme scenario, is the strongest GLE that we ever observed. So during a moderate GLE, the effective atmospheric cutoff energy will be somewhere between them, between the 400 and I would say 300. So, and another short motivation for this study was that there were two definitions for the sub-GLE, one's proposed by Osku Raukanen and co-authors, and they say that sub-GLE is an event, solar genetic particle event with the energies around higher than 300 MeV. And we proposed another definition, the observational one, saying that the sub-GLE is the event seen only by high altitude polar neutron monitors, but which is not seen by even polar, but sea level stations. And our calculations show that actually these two definitions, they agree quite well, and there is no problem using them together. So, and here is my summary. What we did, we calculated the altitude profile of the effective atmospheric cutoff, how it changes with the altitude. We calculated it for the list of the polar neutron monitors. We show how the effective atmospheric cutoff energy reduces during a strong sub-GLE. And we also show that actually two sub-GLE definitions, they by Raukanen and Polyanov, they don't contradict with each other. So they agree quite well. And this is actually all what I was going to say. Thank you.